Am I audible?
Yeah, hi Sunana. Good morning. Yeah, you're
Hi.
audible.
Yes, a very good morning. A very good morning to everyone, and welcome to 11th day of the Deep Learning Summer School by IIITDMJ Jabalpur. I am Sunana Singh, and it's my pleasure to chair this session. I hope you all are enjoying the sessions so far and practicing along with the sessions. Today, we're glad to have Mr. Rushendra Sidibomma with us today. He has completed his BTech in computer science with honors from IIIT Sri City, and his research interests include trustworthy machine learning, LLMs, and computer vision. He has also conducted research during a fellowship at Toronto Metropolitan University. Currently, he works as a machine learning research engineer at AutomationEdge Technologies, focusing on intelligent document processing. Thank you, Mr. Rushendra, for joining us today. I now request you to kindly take over and begin the session.
Yeah, thanks Sunana for the introduction. So yeah, I'll go ahead and share my screen. Are we waiting on some other participants or is that it?
The participants will join in. I've also dropped a message, so they'll be joining in very soon.
No worries. So I can start, go ahead and start.
Yes, 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 you can start.
All right. Okay. Yeah, I hope my screen is visible.
Yes, yes, it is visible.
Okay. Yeah. So all right. So just a quick question though. So I mean, I think this I did have a few small idea of it. Was so what is the audience consist of? So are they grad student, bachelor students, or something like that?
Sir, it is a combination of students and industry professionals as well as some faculties. So all of them are there.
I see. I see. Okay. Okay. So hopefully, yeah. So hopefully, this is not too basic for them. But yeah, all right. I'll start and go ahead. Okay. So hi everyone. So my name is Rushendra Sidibomma, and today I'll be presenting large language models. So I'll be talking about them and a few components in there. Yeah. So just a quick introduction. I think Susanena gave a good enough introduction. So I graduated from IIIT Sri City with a CS in CS with honors, and so uh, my research supervisor was Dr. Rakesh Sanodia, who's kind of organizing this event. I had received a research fellowship during which I was at Toronto Metropolitan University, where I was conducting research on trustworthy machine learning. And so I'm still part of that group that is Trustworthy AI Lab, where I continue to work on research projects. Then after graduation, I started working as a machine learning research engineer at Automation Edge Technologies. And yeah, so my research interests are primarily lie in trustworthy machine learning, computer vision, language models, particularly in areas like reasoning, weakly supervised tasks, and low resource tasks, again, where we don't have sufficient information or label data, right? So yeah, so I think I would about this presentation, how we can take this ahead is please try to be super active in chat. So I initially I was hoping that there will be more students. So I mean, I'm yeah, hopefully the people from the industry won't have too many questions on what I'm starting out. So yeah, you can ask questions at any point of time. The chat window will be on screen. So I have another screen over here where I can see the chat window. So please feel free to put down anything in chat. Uh, okay. So, okay, I think someone already mentioned that there are masters and scholar students. Okay, okay. So yeah, then we can have obviously have quick tangent discussions over here, right? So if I come out of on something and I break out of it, you can always have some leading questions and have questions where we can discuss on tangent, right? And then we can again have reasonable sidebars are okay, so we can push the longer discussions towards the end if that's okay. And yeah, So if the question's too long to put down on chat, I can always unmute you. Hopefully I can do that quickly. So yeah, can. So yeah, so I think we're ready to get started. Any questions before we start? I mean, ideally this would come at the end, but I mean anything that you would want to ask before we get started. Feel free to put it down in the chat. None. So I mean, even if there's none, someone can just put down none so that we can get started. One person. All right. Yeah. Thanks, Abhinav. Yeah. Yeah. So, are LLMs used in geospatial area? So I think we're not there yet right now. Yeah. So I think that's one area where I've not had too much experience and something. So yeah, I'm assuming I think we'll ultimately get there, but I think we're not there right now. Yeah. Hope that answers your question. Yeah. Okay. All right. So we'll get started. So I'll start with introduction to LLMs, right? So what are LLMs? LLMs are simply models that calculate the probability of the next token in a sequence, right? Or in our context, a sentence. So ultimately, we see a lot of. Just give me a moment. Yeah, sorry about the disturbance. Yeah, so yeah, language models are nothing but next token predictors. So what we can think of so with so much hype around LLMs, we see LLMs saying LLMs talking about reasoning, doing complex tasks, coding for that matter, right? So that's something that we've been hearing a lot around us. But one thing that we need to remember is that LLMs are just next token predictors, right? All they do is take in the sequence until now, predict the probability of the next token, pick out the most probable one, and then give it out. So if I start a sentence with "Hi, my name is," and then what it does is it takes "Hi, my name is" these words and spits out the next token. Not exactly a word, but the token, right? We'll get that. We'll get into that. So LLMs are built using deep learning architectures, especially transformers, and so the classical examples have GPT and BERT, that is generative pre-transformers, and BERT, right, bidirectional encoders. So yeah, so that they are the basic building components for all the LLMs that we see around us, right? LLMs are not just pattern matchers; they generalize context. This is one really important thing that we need to keep in mind, is that before LLMs came in 2017, or more than 2017, I think it's before transformers came in. Uh, all the language models, all the NLP techniques were primarily based on pattern matching. They're not exactly something that would understand context, right? If you're having a chat with a chatbot, for example, it will not have a complete context of what you've been talking until now. That's what GPT facilitated, and that as a result now we have such great technology in front of us. So like we know, GPT-4 can write essays, summarize legal documents, and answer programming questions. So that's the scope of it, and we'll start getting into the applications and so on. Someone in the chat role of LLM in medical imaging. So we can go there. So I think I'll keep that at the beginning. I'll put a note here, so we'll go to it towards the end. Yeah. So yeah, so why learn about LLMs now, right? LLMs are they're everywhere. We can see the hype around them, and everyone's talking about that agentic. Um, everyone's talking about AI right now, and was potentially them doing all the things for us, right? Programming, building architectures, designing software components, all these things. So the reason we're learning about LLMs right now is because they are central to the wave of AI innovation now, right? So if any possible industry that we can think of right now, so even the ones that are presumably industries which were not prone to automation or something, for example civil engineering and architecture, even these things have started getting into AI, right? uh, a small example, for example, in civil engineering, it's the strength of materials now. What's the ratio, the best design? AI is everywhere, right? It helps everywhere. So learning about LLMs is essential to stay competitive in tech right now, and especially knowledge-driven industries, either it be academia or some research positions in the industry. So, in general, it also helps build AI literacy. So, in this crucial age of generative AI, we absolutely need that, right? And just as computers were once optional but are now essential, knowing how LLMs work is becoming foundational, right? So, initially, I'd say there were probably jobs where a laptop was not needed, but now I don't think I can't think of a single job where a laptop wouldn't be needed, right? So yeah, that's why we need to be learning about LLMs. So these are the brief trend. Now we'll go to the brief trends of LLM development, how they've been pointing towards slowly. So now we have multimodal images, multimodal models. So their multimodal stands for different type of inputs. You can be given text, images, audio, video, right? You can give it anything, and it'll try to make a sense of it. These models are probably the way to go, right? Because the data we accumulate is not always in the textual mode. So sometimes they're in images, they're in text. You have problem statements like captioning images that Instagram uses, right? So all these things, for these things, we need models. So yeah, then open source LLMs are gaining traction. So Facebook, series of models are called LLaMA, is gaining the most popularity right now, right? So that's the first part about it. Next, we can go towards smaller and more efficient models with fine tuning and quantization, right? Are any of you aware of quantization? Just a quick in the chat. That will be great. Okay, all right. So, I mean, definitely we'll be covering that. So, just wanted to get a brief idea of how many are going to, how many already know about it, so that I can. But yeah, definitely we'll go through them in detail soon in the next part of the presentation. Right. Okay. So again, our another trend is focus on safety, alignment, and explainability. So this is really critical, right? Right now, the more LLMs get into our daily lives, like for example, I think there wouldn't be a single programmer right now who's not using ChatGPT to help him with the syntax, to help him with some bugs, help him solve some problems. So safety is really important because we don't want them to be without guardrails, right? So uh, i- any single problem you can think of, there will be a malicious attacker. There will be people who are not who will be using these technologies for malicious purposes. So safety and alignment with human values is something that we really need. And then the explainability again. So um, yeah, so again, can someone tell me very briefly what they can perceive out of explainability, right? Anyone in the chat? Because it's a really it's a research topic at the end, but something that's really focused, even not just in LLMs, but even for vision models and any models that you can think of. Explainability is becoming really the need of the hour. Can anyone say what they can think of when they hear the word explainability? Okay, I mean, interpretation, highlighting the portion. Okay, okay. Okay. Actually, just one thing. Sunaina, can you? Is it possible for us to let our participants unmute? I think since they're less number, I think we'll be able to manage. Is that okay?
Okay, okay, that is not a problem from my side.
Yeah,
Yes.
yeah, sure. I mean, if at all it becomes a problem and too difficult to manage, we can turn it off later.
Sure, sure.
Yeah.
Okay.
All right. For now, I think you can do that. Yeah.
Okay.
Thank you.
I think now the participants can unmute themselves. Someone kindly confirm if you can unmute.
Yes, we can.
Okay. If I guess you were speaking,
Oh,
but you're on
I
mute.
think yeah. Okay, wait. I think looks like I got unmuted. When did it start, or when did I get lost?
It was a while back when I unmuted all.
Oh, I see. I see. Okay. Okay. All right. Yeah, I think I can just start over from here. So yeah, again, integration with enterprise workflows and productivity tools. This is again classic for anyone who's used VS Code knows about it. So you can use of these autocomplete tools, Tab 9, GitHub Copilot. These are all classical examples of productivity tools. Then again, we have ChatGPT plugins. Again, like I said, Copilot, Google Gemini. So whenever you're writing an email now, Gemini pops up, a window of Gemini pops up, and they'll help you, draft your email, make sure you're sending an amazing email, right? So then again, fine tuning and RAG. This is probably one of the most important things. That is RAG for solving a lot of use cases that were previously really difficult to solve. So yeah, these are the current trends in LLM development. So just a quick overview of what how we use LLMs in daily life. We have Google Assistant, ChatGPT, which is almost indisposable right now. Then we have Grammarly, Quillbots to check your grammar, to check plagiarism. Yeah, like I said, your emails, right? So I think, yeah, this should be fairly simple. Again, for applications of LLMs, we have autocomplete in VS Code. You have chatbots, and nowadays I think every website you go to, there are chatbots, right? So these are what are really they're driving the business use cases right now. They're the pinnacle right now. Yeah. So yeah, we'll get started with the transformers and the transformer architecture right now, right? So introduction to sequence models. So how we got the journey from how we got from RNNs to transformers. So RNNs stand for recurrent neural networks. Okay. So we have traditional models like they were initially the de facto method for handling sequence methods, or see problem switching wall sequence. So uh, okay, first of all, can someone tell me what's the problem with handling sequences? For example, we used to have CNNs, right? That's the starting of where vision started for. Now, what's the problem with vision models, and why can't sequences be handled easily? Can someone just go ahead and mute and tell me what they think of it? Yeah, I think someone's trying to direct message me. You can just put that on all channel. That's fine. People, I think it'll be okay for people to know what you're talking. So yeah, so yeah, I mean, like you said, temporal relationships, yeah, but there's one more critical thing is that if you're training a neural network, what's the first thing that you expect is an image, and the most importantly, you cannot alter the dimensions of the image, right? If you're training a neural network model on images that are 28 pixels by 28 pixels, you can change it, right? Your architecture set up in that way, and your model is trained in that same manner. So you cannot potentially change this size. So if you have an image that's coming from a higher resolution, you'll have to downscale it. If you have an image from a lower scale, you'll have to increase it. So yeah, I think people are saying about long-term dependency. I think we'll come to that. That's definitely a problem with sequence models. But yeah, the first part, the most important one, where traditional architectures won't fit in, is because of the unknown sequence. Your sentence can be two words long, 3 words long, or any furthermore, right? So this sequence is what causes problems, and because of which we need some sort of looping mechanisms in our architectures. So that was what RNNs and LSTMs started out with. So, like here, like it said, short-term dependencies are okay. They're okay with short-term dependencies, but they struggle with long-range context. Now, in 2017, transformers came up, and they revolutionized the area of natural language processing forever by replacing this recurrence with attention. And you might be aware of this paper, that is is all you need, by Google Research. They're the first people who've put down the word transformers and put down the architecture. So yeah, so yeah, I think we can go ahead. So just one thing, if just a quick question. So uh, this might be fairly easy for someone who read that paper, but what do you think the paper or the transformer architecture was introduced for? Anyone knows the problem statement for which it was introduced, or what they aimed? It was clear. It was definitely not, just a quick. It was not definitely not for these language tasks that we're using right now. There's one very specific task that it was introduced for. Can anyone say it out if they know? Anyone? For parallel processing, long sequences was a problem. No. So the reason, or not the reason, but the critical problem that they aim to solve was language translation, right? So that is the de facto method that they wanted to fix, correct? So initially that was again being done by these methods like RNNs, LSTMs, but then transformers was introduced to do language translation. For example, you're translating a sentence from English to French to Hindi, anything. So that was the application they aim to solve. Again, there the issue is that you cannot do a word by word translation. There's so much semantic difference between languages that you cannot do a direct translation. So they're maintaining context, understanding which word points to which word, right? So the first part of the sentence can be, I'm looking at a cat, it is beautiful. So it is beautiful, what is beautiful? Getting those relationships is why we needed transformers. And again, we'll get into the architecture soon. So just the classical RNN and LSTM structures. So with RNNs, it was simply you can look at this, the first part of this unfolding RNN diagram. So there, right now it's just one neuron, but you can think of it as them stacked together, right? So you'll have an input and you'll have an output. Now, why do we need this loop? So that we can keep on creating words, right? We give it a sequence. For example, my name is Rushendra, and it'll take that as an input, keep going on with the weights, keep looping until you get new words, right? For one word it'll loop once, for two words it'll loop twice, and potentially, you can even loop another number of times for more complicated words and more complicated sequences. So even to look, this is like a pretty vanilla equation. So then came LSTMs, which aim to solve this problem. So here, instead of a single loop or a mandatory loop, right, here we have input data, we have the previous sequence again. So at every point of time, we're not just dealing with the sequence until now, but we're maintaining the state or the values from the previous hidden state. So that becomes really important in maintaining. And again, okay, I think the classical difference between that in RNNs, the first word you see or the first word of the sequence that you input is always going to be the first, right? It will not be propagated forward. And by the time you reach to the 100th word or the 150th word, the importance or the the weights corresponding to the first word will not be enough to maintain relevance. That is what LSTMs aim to solve. So at every point of time, you have the sequence until now. So using this, you're still able to maintain context. So you're still gonna have a good amount of attention for the first word in the sequence. But again, the problem is this. Okay, we'll discuss the challenges in the next slide. So what went wrong with them, right? Where did they fail? So first of all, sequential bottleneck. This is the biggest problem, right? The scale that we're looking at right now, we have chat GPTs giving you spitting out answers in a fraction in matter of seconds. But these architectures are not parallel, they're sequential. So in every loop, you're dependent on the input or on the output from the previous step. So for example, if I'm doing the first step, I can only go to the second step, I cannot move on to the seventh or eighth step, right? I cannot do them parallelly. So I'm dependent on the output from the previous step to do further processing, which is why we need something to move towards parallelism. Now, vanishing gradients. So this is a very well-known problem in machine learning, right? Long sequences can lead to information decay. Can someone? I think this is a super basic question for anyone who's been doing slightly into machine learning. So can someone just tell me what vanishing gradient? Not probably in this context, but in general in machine learning, what vanishing gradients are? Anyone? Okay, I'm not seeing too many answers. Okay. All right. Okay. So I mean, I'm assuming some of you are, most of you will be aware of back propagation or training, right? In this, someone put up a chart: as network becomes big, the back propagation leads to diminishing learning. So an update after a certain, yeah, criticize, yeah, correct. That is true. So, for example, the classical case of back propagation, right? So, if you're training a fully connected neural network, you do a lot of training. For example, if you make your neural network probably 15-20 layers deep, correct? So then what will happen is the weights that were at the beginning will not propagate, or during back propagation, the weights that were the loss that you have at the last layer will not be propagated until the first layer, right? These loss, the gradients corresponding to that loss will not reach the first layer, and hence the like someone just pointed out in the chat box, the initial layers or the initial weights will not be trained. So that is a very critical problem, vanishing gradients, and there are a lot of techniques to prevent vanishing gradients. Then again, it's hard to capture long-term dependencies, like we discussed. They're slow and inefficient for large data sets. It's simple enough to understand because of the sequential bottleneck. So when translating a long sentence, RNNs may forget the subject by the time they reach the verb. Absolutely, that happens. And even in bidirectional LSTMs, only partially solve this problem because they still have computational limitations. So bidirectional LSTMs are ones which aim to go backwards and forwards, right? There's two components of it, and one part of it is going from the end of the sentence and another is going from the beginning. So again, they again suffer from the same computational limitations. So these are the limitations. Now we will go for the transformer architecture. Now this has actually shifted the paradigm in this area. So transformers attend to every word in the sequence in parallel using self-attention. So okay, we'll go with each part of it. So this is not something that we can understand in a quick on our lecture, but I'll try my best to understand, explain what this self-attention means. So we can start with the key components of this architecture. That is a self-attention mechanism, multi-head attention, positional encoding, and feed-forward networks. So I'll discuss each of these components in detail. Right, the model can weigh the importance of each word in the global context. Right, so we'll start with self-attention. Right, so now what does self-attention mean? From as the name indicates, you want any word in the sentence is obviously so obviously it's going to be relevant to the word before and after it, correct? But how important it is on its own, correct? That is what self-attention captures. So ideally what we do is, for example, we have four words, that is 0 1 2 3 4. I'm just doing the indices. So we pick the first word and weigh its importance with each of the other word, right? So zero with zero itself, that is self attention. And then, I mean, self attention is when it tries to do on its own. And then multi-head attention is where you're trying to compare each block of it, each indice with each of the other ones. Then what typically happens here is that it's like a sliding window, right? Your window is your attention, and you slide it over every single word to understand what is the importance. Now, how do you evaluate this importance? That happens with the training. Right? As you train, you train hyperparameters, you train the parameters, you train the weights, you train the biases. So as you slide down during the training process, they understand where each word is important. Right, that sliding window will get a context of it. And then a very important component again is positional encoding. So the word there is all not just in English language, but in any language you can think of, the position of the words definitely has some relevance to it, right? So we do also include as an input to the transformer architecture the positional encoding, right? So if a word at the 0th index, someone's at the 90th index, you do want to encode that this word is at the 0th and this is at the 90th. So words coming at the beginning may have different context than words coming at the end. So that is why we need position encodings. And then feed forward networks is again to get as a decoder or an encoder. That's something that we've already dealt with in vision models in neural networks. So it's just capturing features, trying to put them forward, right? So this is the diagram from the research paper. Attention is all you need, the paper that introduced transformers. So yeah, this is what I was talking about. So we have inputs, that is input embeddings, right? How many of you know what embeddings are in the context of LLMs or NLP together? think this should be a fairly simple question. I think we can expect some answers. Okay, encoding schemes. I think I'm not sure that's the right answer, but okay. All right. So I can start with, okay. First of all, when you give ChatGPT a set of words, right? Even at this point, does GPT understand words as it is? Just a yes or no question. Can someone answer? Does a transformer model understand words as is? Right? Does it understand English? Yeah. No. Correct. It doesn't understand words. Yeah. Perfect. I think Rajesh Kumar got it right. So they are vector representations of data. Correct. I think now people are getting to the right answer. Correct. So yeah, it doesn't understand English. It understands. It's still even with all this talking we've been doing with ChatGPT, it still does not understand English. It just understands tokens, right? And ultimately what we do is we break down. So the step. I can just let me see if I can put down a chat box, text box. Yeah. So we start with words. We go into tokens. Tokens is how any word can be broken down, right? So not necessarily, if we have a long word, we don't always call it one token. A word can have multiple tokens. Then once we get the tokens, we convert them into embeddings, right? And what are embeddings? Like we take, so embeddings are vector representations of this word, of this token, precisely like someone in the chat box mentioned. They're very exactly a vector representation. So an embedding for the word I, or for example the word strawberry, would be a, a matrix which has uh, something, for example, a lot of values. And ideally right now we have these embedding models which have 1536. These are dimensions, commonly known dimensions. So the word strawberry is a vector represented by 1536 numbers, right? This is the common size for every word in English, so that has to remain uniform. So that is what embeddings are. Now this embeddings is what transformer understands. This embeddings is where it tries to make relationships. And now, can someone tell me what the most critical part of these embeddings are? I think that's, if I'm not wrong, the only that's probably the most important one, right? It's the reason embeddings were created. Can someone tell the most important aspect or feature of embeddings? Okay. All right. Okay. So I think to put it in some other way, I'll say, um, so prediction relation capture semantic relationships. Exactly. Yeah. Capturing semantic relationships. That's the most critical part, right? Exactly. So now, uh, to put it down in layman terms, right? So for example, we have the word animal, and then we have the word cat. So now, okay. So how do we compare two vectors? What is the similarity we use for comparing two vectors? So you might have heard of cosine similarity, right? So cosine similarity is how you compare two vectors or how similar they are, correct? I'm assuming, since I mean, if you're at least undergrad students, I think you might be aware of cosine similarity, correct? Yeah, yeah. Okay. So cosine similarity is what you use to compare vectors. Now you can always know that one vector is similar to another by doing the cosine similarity. If it's a high value, then they're more similar. If it's a low value, they're less similar. Now, these embeddings, that is the most important part of converting them into vectors, is that now these embeddings can be compared to each other. So the embedding for the word animal will definitely be closer to the embedding of the word cat more than the embedding for the word car. Does that make sense? So this is what has to be captured. That's why these vector representations, you cannot make a vector representation on your own. I cannot make one on my own, right? That's something that has to be standardized up to a certain extent, because these embeddings have to make semantic sense. So that's where we start with, right? So then we put these input embeddings. These inputs are converted into embeddings. Then we have the position encoding, where it's an encoding of things at the beginning of the sentence, position of each word that we're passing through, and then it goes into this attention blocks. So now the reason there is n times on these blocks is that you can propagate them, you can put them stack as many as you want, right? The GPT architecture that we see, or the chat GPT that we use to on our web, is probably consists of thousands of such blocks, or even much more, right? So this is where multi attention comes from, where that's like a sliding window which brings attention to every single word, goes on top of it, and finds how important it is in this current context. And once that happens, it is fought to the decoder. So this, until now it was encoder, and then it is passed on to the decoder. Now this decoder will try to someone put in a message in the chat: input embedding schemas are constant or fixed. Input embedding schemes, I'm not sure what you mean by schemes. If you mean the dimension of inputs, that's it can vary, obviously, because we're talking with text, dealing with text. But if you mean the schema or the weights, but for inferencing, obviously the weights will remain same, right? I'm not sure I get your question exact. I hope I've answered your questions. If not, you can just put down again. So yeah, so the first we have the encoder part here, and then next the decoder part. Now again, we have to understand that within these blocks, we're only dealing with vectors, right? So once we have these multi-head attention, we find out which vector is the most important, and scale them accordingly. Then we'll have the decoder part, which will again take these vectors. Now we are in the process of generating text, right? So we need to take into consideration how important each word was, understand what comes next, predict the next token, and then again put. Now with the decoding part is when you're generating, the encoding part is when you're trying to make sense of the input, and the decoding part is when you're trying to generate output based on what you've learned until now, and considering the context that you've been passed the input. Then they come out, the same attention again goes through each of the output ones, and then you generate tokens. Like I said, each block of this transformer is just a next token predictor. So then you have again the classical softmax function. So it calculates which word is most likely to come next, and that'll what be selected. So for example, if I say the cat is on the window, so that becomes the input. After all the processing, it can continue that sentence by saying the cat is on the window sleeping. So it'll have a lot of words that it predicts, and out of them, the most probable one is what is predicted in the next. And after, to generate the next word, again, it will take the cat is on the window sleeping. That becomes the input, and then again we'll have an output next word for it. So that's how an architecture, that transform architecture, gets the next words. All right. Okay, so again, there's a lot of math. There's a lot of very complex topics for this to understand this transformer. But this global attention is what is making them so powerful, right? That because each word gets all the attention that it requires. So each word attends to every other word through this attention scores, and long range dependencies are captured instantly. So this probably is the single most critical equation in designing the architecture. So I don't think we can get into it too deep right now, but this is something I recommend everyone read. So I'll get to the paper details in the next slide. So yeah, again, the next point is that it enables better representation of context, grammar, and meaning. So here, like we talked in the beginning, they're not just pattern matchers. They're not going to spit out words that they've already learned. They're going to make sense of it. They're going to capture relationships. They're going to capture grammar. They're going to capture context, and uh, and generate very new, very relevant information again, right? So the cat that sat on the mat was black, was and so the cat and not mat. This is the thing that we talked about. We need to understand which which verb or noun it corresponds to. So attention lets the model dynamically decide which words are relevant. So this is again all thanks to the data that input data. So we need to have the training data to be really capture all the relationships that we wanted to, right? Yeah. So this paper it's what led to it all. So this is the attention is all you need paper by Dr. Vaswani. So you can go through this paper. This I've attached the link. I'll share the slides after presentation. And if someone just wants to do that while we go through it, I'll just put it in the chat box. Right. Yeah. So now we'll go with the parameters of an LLM. So we've all seen. Now we can kind of get a sense of what LLMs are, right? So now we want to understand what each of its parameters are, the type of configurations, or if I'm hoping that's the right word, configurations that we can run the LLMs in. So yeah, what are parameters in language models? Parameters are weights or unknowns that are learned during the training process, right? Just like we have in a, I think I'll take an analogy of a classical neural network each time, because I think everyone must be aware of that, and that's something that we can relate to very easily. So parameters there would be the weights and biases that we're training in a CNN or a neural network. That is what, again, every single deep learning model is based on the learning of these parameters. So that's what we learn in these language models. So they encode the model's knowledge and determine how it predicts the next word. So even if you throw off a single weight, your LLM may not be working as expected. So the more the parameters, the greater the capacity to capture language patterns. But again, this is not all. More is not always better, right? So again, classic analogy to the neural network. If you make a super huge 4-layer, 5-layer, or even 10-layer neural network, right? You'll be able to capture more relationships. It'll be able to perform better. Not always. You obviously have to take care of some hyperparameters, but you can in general assume that if you have a complex task, a bigger neural network will do better than a smaller one. Just like that, we move on to GPT-2, which was in the initial states during 2020-21, where it had 1.5 billion parameters. GPT-3 moved on to 175 billion parameters, and the GPT that we use on the web right now, even some predict that it's not an open source model, so we're not sure of exactly how many tokens parameters it has. But I mean, some research does suggest that it can lead upwards to 900 billion parameters. So you can imagine the scale at which it's operating, right? So the more parameters means more computational more complexity, but again, it also leads to higher computational cost. Okay, so moving on to the, so how much memory does an LLM take up? So here I want, we'll discuss this slowly. Okay, we'll take it slowly, and I want to hear some answers from you. So let's say your model has a 20 billion parameters. How much memory will it need? And so first we'll look at the questions that we need to want to consider. How much memory will it need? Do you need all that memory in RAM? Or, and last question, is the required memory just the sum of all the space taken by the parameters? So we'll go one by one. So how much memory will it need? I think we don't need a numerical answer, but I think we can start with, do you need all that memory in RAM? So what do you guys think? Do you need, for example, we have a 20 billion parameter model, right? Do you need all that space in RAM? Be great if someone can answer. We'll see. No. Okay. So what will happen if not RAM, then for example you have this is not an exact answer, and we'll definitely go with how much memory it will need. But for example, your 20 billion parameter model needs 50 GB of RAM, 50 GB memory. So if not all in RAM, what will happen? What will happen if it's not in RAM? What's the consequence or implication? Anyone? It's share storage using segmentation, process slow. Yes, it will be slow, but I'm not sure if I understand your answer, Megha. So it shares storage using segmentation. Not really. I think the idea is a little off. Anyone else? Any other guesses? It's exactly what happens when for example you only have 1 GB of RAM in your phone, assuming that, and you have 20 applications open. It's not that your phone will stop functioning, right? I mean, it'll get tremendously slow. That's true. But what happens internally? Yeah, exactly. Using secondary memory. Perfect. Yeah. So that's the answer we need. So if you cannot fit all that memory in RAM, what happens is will again due to, the only reason we can leverage this is because of the parallelism. So we can uh, inference a part of your text, keep the part of your a part of the model in your RAM, inference it, get the output, switch that part of the LLM to another part of the LLM, that the next part of the LLM, and then bring it into memory, inference it, join it with the previous output. So this is what happens, right? Even in our phones, even in India, any other applications, you use secondary memory, correct? You keep you don't you're trying to load a file of 12 GB. You only have a RAM of 8 GB. It first loads the first 8 GB or whatever is available, gets the output, processes it, brings it out, gets the remaining 4 GB out into the RAM, and then process it. So that's what happens even here in LLMs. Okay, next question: is the required memory just sum of all the space of all the parameters? So for example, we had 20 billion parameters. So does the memory requirement of the LLM just the sum of all these 20 million parameters? Again, okay, no. So what else could it be? What else could lead to additional space requirements? Okay. All right. I mean, okay, that might be something intermediate activations. Yeah, you're partly right. That's true. Intermediate activations do take up some memory, but yeah, we can discuss what happens. So yeah, for a 20 billion model, now we'll get to the answers to those questions. Okay. So the size of each parameter is 4 bytes. Can someone tell me why it's 4 bytes? Think I'm assuming most of you are from a CS background, or at least a good part of you. So why is it 4 bytes? Why is the size of each parameter 4 byte? And can it be slower? Can it be smaller? Or can it be higher? Okay, I'm not getting too many answers. Okay, so all right. The first question would be: does everyone understand floating point FP32, floating point 32 bit precision? Okay. All right. Okay. So in simple words, it's like the precision to which you can calculate a number, right? So for example, you have the number, for example, 23.567, and it'll go on until some 7-8 digits, right? You want to be able to keep all that precision. Ideally, you would want to keep all that precision, right? You don't want to round that off to 23.41. That's all. You're losing all the data after it. And when you're dealing with such a scale, and when each word of your generation is really important, you ideally want to maintain all that precision. So to maintain all that precision, the most or at least the ones that are commonly used is an FP32, 32 bit represent 32 bits, which is 4 bytes, correct? So that's how much each parameter will take up, each weight, each bias, or anything, each of your parameters. Now the size of a model in bytes would be 20 billion times 4 bytes, right? So that'll be around 80 GB, correct? So that's how much you will need it, right? If you're using on full precision, correct? So 80 GB for a 20B model is so 80 GB is not something that you can find in your regular general purpose computers. So you'll need specialized hardware for that, and that's the reason we could ultimately get this down to 2 bytes by using FP16, or even lower, even below FP16 we'll have integers. So you would ideally round off every single weight. For example, if someone weight was 23.485, you would round it to 23. So that will take up much less space, and it will reduce the space memory requirements much down. But again, you compromise on training accuracy, or you compromise on accuracy in general, or the quality of generation. But yeah, like I said, the memory taken up by other parameters like the keys, the k and v, the queries, and all these values that we discussed, right? So for that, we'll need additional memory. So the common convention is to approximate the memory required as 1.2 times the space taken up by the parameters. So our 20B model will need a 1.2 times 80 GB, that is around 96 GB. So again, we don't need it all in RAM, but it will be painfully slow if we don't have it all in RAM. It will be super slow. The inference will take much longer. So yeah, this is about how much memory an LLM will take up ultimately. So now we'll discuss about the configurations or the settings in which we can operate the LLMs, right? So I think settings would be the best word to it. Context window. So a simple question. So if you give ChatGPT your entire textbook, right? For example, you have a 200-page textbook. If you give ChatGPT all 200 pages, will it be able to summarize? And you ask it to summarize all of it. Can it do that? You can put down your answer in the chat. Okay, one person said no, it does, but it misses a lot of things. Okay, no, I guess someone says yes. Um, so yeah, the answer would vary or fluctuate between no to it misses a lot of things. So sometimes ChatGPT, I think I'm not sure if you guys have experienced it, but after a certain point, ChatGPT does not accept input. So their web chat does limit you to a certain number of input tokens or input words, right? So that is one aspect of it. And second aspect of it is, right, it misses a lot of things. So if you give it so much context at once, even then, at that point, the global attention will fail, right? Because you cannot do it on every single word for 200 pages. The attentions will make less sense. More important, I mean, it can, you, if you have the hardware requirements, you can do that, but it loses sense of the word attention because you have way too much words. Obviously you can have a lot of parts will be important, but when you're forcing it to prioritize a few things, it cannot get a complete idea, right? So that's the reason. So that is, so every LLM will have a context window, which is like a reasonable limit, after which, so is a reasonable limit for a single prompt or a single instruction, right? It defines how much text a model can consider at once, in simple words, right? Which is again measured in tokens. So a model with small context window will forget the beginning in a long document, whereas ones with very high context windows, for example, the latest models, if some of you might be aware, like GPT-4 or the advanced models like Claude and Claude by Anthropic, right? So these models can go until, or Gemini are claiming to go until 1 million input tokens as context window. So that's a huge improvement over what we had initially. But one thing to remember is that even with 1 million context window, things said at the beginning will slightly lose context. So under reasonable considerations, we would want to keep this context window lower when we're trying to inference it to get the best results. Okay, so initially GPT-3 was 2,408 2048 tokens, and GPT-4 can now accept until 128,000. So you can see how much of a difference or how we scaled up. Now, for important tasks like summarization, reasoning, and code understanding, we need to absolutely consider this context window. Like the example that I just mentioned. For summarization, you cannot give it a 200-page document and ask it to summarize it. You would ideally want to take it slow by having 20 pages, 30 pages summarized at once, understand a topic, spread it either topic wise, page wise, or anyhow. So the newer models can even handle entire books, like I just asked, but again, you will slightly lose context and the results will not be great at reasonable, right? Now, temperature. So this again might be analogous to the temperature that we have in traditional AI models. Where this temperature is basically the stochasticity of the system, right? It's about how random you want it to get. So, does any one of you? Okay, okay. How many of you know have heard of this? Again, the training called the gradient descent. This, I think, I'm hoping to get a lot of answers for this. Are you aware of gradient descent? Okay. Correct. Yeah. So gradient descent is when you have all right. I think I'm not sure I can draw here. Yeah, problem. Okay. So with gradient descent, so ideally, if you want to get the correct answer for a gradient descent, right? You do gradient descent and you want to arrive at the most optimal answer. You have to find the minima of the function that your network creates. Now, even there, temperature is used, but to a different extent. So, okay, let me see if I can try to draw out over here. Okay, yeah, I think this will go good. This might be able to. Yeah. All right. Okay. Oops. Okay, so we'll look at this curve right now, right? So right now, if we okay, so right now I'm not able to get rid of the cursor, but okay. So you can look at here, right? Uh, if you have at two, you can put a ball over here, right? You can consider this as a visual representation. You can put a ball on top of this hill. Where will it roll down? It'll roll down to this part, right? So this will be the minima that it achieves. But if you put down a ball over here, this will be the minima that it achieves. So here, the global minima. So when you're doing gradient descent, you want to reach the global minima, which is this part in this space that we're assuming right now. Correct. Now, but for example, if the starting point is here, if your parameters were designed and your system was designed such a way that it will start here, you'll only reach here, which is not the system that we want, which is not the result that we want. So this temperature can be analogous to that. So we have this gradient descent with momentum, Adam optimizers, all these new age optimizers. We can, so for example, when you reach a global minima, it'll give you a push. It'll give you a push to a certain extent in a particular direction. Now it's not always fixed. You can have it in any direction, and it can be randomized. But if assume at this point you are here and you give it a huge push, and it jumps over here and tries to get here, right? So then these random pushes are is what momentum and all these aspects are covered. So here, just like in temperature, if you want a very deterministic safe answer, right, you can keep 0.1, where if it lands at a minima or if it lands at when it's predicting tokens, if it finds the most probable one here, it'll stop. It'll give you that prediction. But if you keep it a high temperature, even if it were to land at a local minima, it'll probably give it a push, has some stochasticity, add random a push to it, which would potentially lead you here in an aim to potentially lead you here. You can always guarantee that it'll go to a local minima. So that is how I can just bring this. Yeah, so that is what temperature is, right? So if you want creative tasks where you don't want to, there is no right or wrong answer, right? For a creative, if you're asked to create a poem, right, there's no right or wrong answer. So there you would want to use high temperature. This is associated with creativity, right? It'll try out new combinations. It'll try to explore more different corners. Whereas if you have low temperature, it will be a very deterministic, safe, factual answer. So can someone give me an example where you would want to use low temperature? Anyone in the chat box? Okay. I mean, like I said, I think you can put it in the all channel. You're putting a direct message to me. I think you don't need to do that. But someone said weather prediction, scientific calculations. So yeah, so something like where you don't want any scope for mistakes, right? For example, a right answer would be like when you're trying to, obviously you're not going to make an LLM do your math calculations, but when you're asking, by chance, if you ask it for what is the value of 2 plus 2, you don't want any non-determinism, right? You always want a correct answer, and you always want a relatively reproducible answer. So formula wise, it modifies the softmax function to make the probability sharper or flatter. Correct. So when it's flatter, you can explore more. When it's sharper, you don't want to explore more. You will go with the one which has the maximum probability. So for coding and summarization, you use low T, because even with code, you don't want it to make up random syntaxes. But for poetry and story writing, you will use high temperature. Yeah. So another thing is top P. So this is similar to temperature. So the thing is, as a common convention, both top P and temperature, you don't want to alter both temperature and top P at the same time, right? Top P controls how many probable words a model can choose from. So okay, someone asked in the question, isn't local minima a less accurate test result? No, local minima is what you want to achieve, right? That'll give you the best results based on the loss function you created. So if your loss function was designed correctly, the local minima would lead you to the most probable or most desirable answer. So anyways, coming back to this, nuclear sampling is again how many probable words the model can choose from. So at the final, sorry, I think so yeah. So in the with the top in nucleus sampling, what you'll do is you'll pick the k words, right? Instead of picking from the top k words, you can set up a dynamic set of words whose cumulative probability is less than p. So in other words, you're altering the words from which it chooses from. So by default, if you have 10 words that it chooses from, correct? So if you increase it to 20, there's always a probability that some a different set of words can be chosen, right? So if in your default model you have 10 words, then you can go to 20. If you put it to 20, it'll become, it's the equivalent of having high temperature, right? Where you can have more creative words. You have the choice of getting more creative. Where if you reduce the number of top p, right, if you make it lower, then it means it's reducing the scope of words from which you choose from. So higher top p gives more diversity, can risk hallucination, and lower top p is more conservative, just like temperature. So since these are very close to each other, so temperature and top p ideally are not used together. If you use top p, you don't need temperature. If you use temperature, you don't need top p. So yeah, coming to quantization, this is again a very important thing. Like we discussed in trends, in the recent trends for LLMs, quantization is very important. Again, we'll discuss why. So quantization reduces the precision of numbers used in the model computations. That is from 32-bit floats to 8-bit integers, right? So this is what we discussed a few minutes ago, right? So if you want the most precise one, you will want to use 32-bit floating point uh, uh, floats, which will take up 4 bytes. Whereas if you use a simple 8-bit integer, it will just be 1 byte, correct? So you can reduce it to that extent. This leads to drop in accuracy, but they can be managed using the following ways, correct? So first, we have two types of quantizations, which can be post-training quantization and quantization-aware training. So uh, as a brief idea, so what do you understand by post-training quantization? I think as an intuition, that should be fairly easy enough. So what do you mean by after? So during my training, am I doing? So during my training, is the model the same size, or am I reducing the precision? Okay. So someone said after training, quantization is done. Yeah. So during training, I'm using the full precision. So someone said we train the model for full precision and on deployment reduce. Absolutely. Yeah. That's how we can sum it up, right? So during the training, we want to be able to capture all the possible relationships to the most possible precision, to the most highest possible precision, right? So there we leverage that during the training, but when you are deploying it, or yeah, again we're inferencing it, we reduce the uh, precision. Now this is particularly risky on some level, correct? Because it was trained to deal with high precision, and when deployment, if you're lowering the precision, it can lead to unwanted results, it can lead to hallucinations, and it can lead to a lower quality of results. But again, it's like a trial and error method, and you can always optimize these things, and you can make it, instead of reducing it all the way down to 1 byte, you can make it 2 bytes instead of 4. That will still reduce your memory by half. And for tasks like classification, you might be able to quantize the model to a good extent without harming the accuracy or deteriorating it. Next is quantization aware training. Again, I think this is intuitive enough. Can we get an answer for yes? None. Converse to the post. Um, Not really a converse though, because you're not gonna quantize it, train it, quantize, and run it in full precision, right? That's the opposite of the previous one. So yeah, so I mean, to answer that, so it's technically you're quantizing in both. So even during training, you have a quantized model, and even when you're inferencing it, you're using the same model. So basically, this is the most efficient in terms of memory requirements, right? You have a quantized model. Yeah, you have a model full precision one. You're reducing it to a lower precision model, and then you're training it that way and inferencing it on the same model. So this will take up the least memory, and this is probably a higher chance of succeeding, right? Because you're training it on quantization. So again, here you might lose the reasoning capabilities or the capabilities to which it captures relationships. But again, when you're fine tuning, this might be a good approach, since you know what exactly what you expect, right? For a generative task, you may not want to do a lot of quantization, but for very specific fine-tuned tasks, you can do quantizations and find a good balance between them. So it is absolutely popular when deploying ML models on edge devices like mobile or cloud, right? You cannot have 20 GB RAM on your mobile, and even if you do have it, you cannot allocate it all for this one inferencing. So that's where quantizations come into picture. Think of it of using like a rough estimate instead of the exact numbers to speed up. Like that's another way to put it, right? Yeah. So the performance benefits of quantization. So it can lead to up to 4 times reduction when converting from FP32 to int8, right? So that's uh, getting from 4 bytes to 1 byte. So you can get to 4 times reduction of space. Faster inference. Integer operations are faster and hardware efficient. I think people who might be aware of computer architecture can connect to that. Again, lower memory usage, so less RAM and bandwidth needed to run the models or load them. Energy efficiency, that again critical for mobile. You can't have a full scale model running on your phone and expect the battery to hold up. This is why quantized models are used in apps like Google Translate on on-device assistants. So right now with all the new coming up, the model, uh, if memory requirements are huge, the energy or power requirement will be even worse. Yeah, that's always there, right? If you're using more memory, it'll take more CPU time, more time to read those, put it into memory, bring it out, and put the new memory in. So yeah, so which is why quantized models are mostly used. So for example, the model that is there when you're composing emails, right? You have this recommendations button, you have Google Gemini trying to help you out. So they are not full-fledged models. They are models for this particular fine-tuned task, and they're definitely quantized because they would want to run that on your system, correct? So yeah, these are the aspects. Now we can go towards efficiency gains, which I think we kind of covered it. So like we said, we can get 2 to 3 times faster inferencing time. Operations are faster, sir. So always the pre-trained data is FP32. Abdul, so I mean, someone asked, are the pre-trained data always in FP32? So I think it's important to note here that the data is not what we're looking at, right? The whatever we discuss FP32 is the model. The So you can always consider. I think this holds for any deep learning model. So the model, how we can imagine the model is a suitcase of weights, right? Models are nothing but weights and biases. So the model is what is trained in FP32, and not always, right? You can get it down to integer 8 or FP16, train the model and inference it. So to answer your question, it need not always be in FP32. Yeah. So again, popular tools like Hugging Face Transformers, TensorFlow Lite offer a lot of quantization options, so you can make your workflows efficient. Now, the drawbacks and challenges of quantization. So one is, like we discussed, the accuracy loss. Some models degrade in performance, especially in sensitive tasks like medical and finance. So these are places where you don't want to rely on quantizations. So I think Abdul put down a question. So why don't we initialize the model in int8? So like Abdul, you can always do that, but if you start it in int8, you can go towards FP16 or 32 later, right? Because your model learned to only uh, was trained to understand only integer eights. So you giving it a more precise one will not be able to. The model won't be able to leverage it. So you using higher precision later on won't even help. So I hope that answers the question. So yeah, difficult to quantize all layers. So some layers like softmax are again harder to quantize effectively, right? So some layers, not just softmax, but some intermediate layers may have some really important weights, and if you quantize them, you might even lose the essence of the task that you're working on. So limited support for quantization are attending in some frameworks. So yeah, this is more of a engineering aspect where if you're using a framework which don't allow you to do that, that is also possible. Yeah. So then we have hardware compatibility. Not all GPUs or CPUs can accelerate int8, right? This is again a question. So even if you bring them to int8, not all hardware systems can accelerate or make it much faster as the ones that you want them to. So one word of caution for this quantization. So quantization isn't a plug and play in every case, right? It's not like uh, something that you use. For example, you have a 20 GB model, you want to make it 4 GB or 5. You just use quantization straight up. That's not how it works. You need a lot of trial and error. Retraining may be needed too. So these models need train on narrow distributions with sharp decision boundaries may suffer more from accuracy loss. Uh, so someone asked, if I want to deploy a model on FGPA, then it must be quantized and fine-tuned for a specific task. I'm not very sure what you mean by FGPA. I'm not sure if it's a framework. It's something that I haven't worked on. If you can elaborate that, I can answer that better. So when do we want to use quantization, right? Is when we are deploying on edge devices, right? So when you're relying on this, you can use that. And when is it great for? Speech recognition, image classification. So like I said, classification tasks, we might be able to, it might be, they might be able to do a good job, because it's not about a generative task where you need to get every single word straight, but it's about classification. Again, when you need a trade-off between speed and memory, versus a slight potential drop in accuracy. So this is again what you have to take into consideration. And then the future trends are where mixed precision inference. So this is what we ultimately want to go towards, right? Some weights are more important than the other. If we there is research about finding out which weights are more important than others. You can take a look at that. So for those weights, you can have an FP16, and for the less important weights, you can have an int 8. So this is where we ultimately want to go to, right? That'll be great for memory savings without having a significant drop in accuracy. So now we'll go to training. How are LLMs trained, right? So language models can learn to predict the next token in a sequence, right? That's what they do. Now, this can be done either in a self-supervised learning or a massive corpora of data. The core idea is to convert large text data sets into input-output pairs without manual labeling. So all of you are aware that manual labeling is expensive and slow. So GPT was not trained solely on manual data. So when you look at the amount of knowledge a GPT has, the reason it could do that is because it has been trained on to a certain extent all of the internet, all the data that's been available on the internet, at least publicly. So the core idea is to convert these large text data into input and output pairs without manual labeling. The process goes as tokenization, a forward pass, loss calculation. Based on that loss, you do the back propagation, and the weights or the parameters update. Right? This is nothing different from what we have in a typical CNN or a fully collected layer. Now, LLMs don't need labeled data; they just need a lot of raw text. So this is particularly this. To make a sense of it, for example, if I have 20 pages of data and I want to fine tune my model on that, so I don't need to explicitly create unless I want a question and answer pattern. I can just give all the corpora to my LLM and train it in such a way. It's just some engineering aspect where you just try to uh, LLMs will just predict the next token, right? So you give it the first 4 words, ask it to generate the fifth word. Give it the first 5 words, ask it to generate the sixth word. You can create training data out of corpora without manual labeling. So that's one really interesting aspect of getting training models for fine tuning. So these training sources can come from Wikipedia, Common Crawl, GitHub, and all the sources that you find on the internet. So moving on to base models, this is the foundation of all tasks. So the model that you have on GPT, right, that you access on the web, is the base model. It's not something that has been fine tuned to do a task. It's a general purpose model. So you ask it to do some math operations, it'll do a reasonably good job. You ask it to do some classification task, it'll do a reasonably good job. So it's not designed or trained specifically for one task, right? So base models are trained from scratch using general purpose text. Like I said, you can just design the input in such a way that you can keep on training on the same corpora. Now, no specific fine tuning trained with a single objective. It's just like a next word prediction. Examples are GPT-3 base, BERT, LLaMA, all the models that you can think of. They act as general purpose learners. So it's like a general. For example, it's technically like the internet. You search whenever you search for something, you get it, right. It's not that you're gonna when you click on some website, you will be able to get some particular information about it. That's the analogy that you can do, right. Base models are like the internet. You can just find what you need, but if you want to dive deep, you will want to go to one specific model or a specific website, which are basically fine-tuned models. So you can think of them as a blank canvas that understands language broadly, but doesn't specialize in any task. These are the raw form models. They can be customized. Now you can fine-tune them and customize them for chatbots, summarizers, translators, or any task you want. So don't need label data. It's called unsupervised learning. Someone put it. Yeah, so that is true. It's called unsupervised learning, but that's right. So I think I didn't cover that point. So when you're talking about supervised learning, that will be for fine-tuned tasks. So when you're trying to make an LLM classify whether your sentiment, for example, given a sentence, it has to detect whether the intent of the text is good or bad. That is a classifier, right? There you want supervised learning. There you'll use supervised learning, so you know the label. You need some label data. But when you're training on a corpus of data, such as asking it to learn a textbook, there you don't need labeling, so that becomes on some level unsupervised data. Yeah, unsupervised learning. So fine-tune models, now this is where we want to adapt them to specific tasks, right? So here fine-tuning means training a base model on specific data sets. It uses supervised learning or reinforcement learning, like you mentioned, right? Here we want some training data, and if that is not enough, we need some reinforcement learning too, which we'll discuss slightly towards the end of the discussion. So instruct models are different from base models. So how many of you have heard of instruct models when you came across LLMs? Any of you know what instruct models are? I mean, the answer is pretty much here, but I mean, if you have some experience with them, okay. So not too many, I guess. So yeah, so instruct models are models that are trained to follow instructions. So when you are asking GPT to do something, a big task, for example, something that's not too simple, right? You want it to follow your questions. You don't want, for example, you ask who was the fifth president of the United States. Now, if it were if it were a base model, it would go on forever. It not forever, but it would go on for three paragraphs. It will say that the fifth president was so and so. He did this. This was his childhood. Probably like a Wikipedia article, right? But when you want it to be a question or answering bot, right? So there you want it to stop. For example, if someone asks who is the fifth president of India, or the states, you want it to give the name and then stop, right? You just want an answer. You don't want the entire biography of that person. So these are tasks where you want instruct models. So again, chat GPT that we see on the web is on some level trained for an instruction task. So it won't keep on going. You might have noticed that sometimes when you ask a question, it'll keep on generating. It doesn't stop. You know you got your answer, but it won't stop. That's potentially because you can have both a base model and fine-tune model, right, at the same time. So it serves different users differently. So that's how it works. Fine tuning teaches the model how to behave for a particular use case, that is chat or translation or classification. So RLHF involves human ranking responses, guiding the model toward preferred behavior. We'll definitely discuss this towards the end. We have that topic over there in the presentation. So the key differences between base models and fine-tuning models is training data. So for base model, the training data is general corpora. In fine-tuned model, it will be a task-specific data. So it will need labeling. So like someone was asking, so base model does not need any labeling data, and fine-tuned model will need some label data. Objective is the next token prediction, as simple as that, nothing too complicated. But with fine-tuned model, you do want the next prediction, but you also want to align with the objectives of the task. The task is to classify a sentence as positive or negative, you have to say that, or as a positive sentiment or a negative sentiment, or you want to capture hate speech, or you want to detect whether some part of the text has hate speech or not. You'll need that to align with that. Then behavior of base model is raw and general, whereas with fine-tuned models it will be goal directed, aligned, and it will be concise in most aspects. So the usage for base model just needs prompting, whereas for fine-tuned model, since it's for a specific task, it assumes that that's the only task that it has to. So when you're fine-tuning it, it will only give an answer corresponding to that particular task, right? So this is a really good example that can be used to determine the difference between the base model and the class. So you must be aware of those huge manuals that come in when you buy a car or a bike, right? No one reads them, correct? No one has. I mean, I think some particular person might, but in general, we're not able to read all of them. We prefer not to, right? So what if we train an LLM on this manual and let the user ask questions? What will happen? So first now, let's assume we're training it as a base model, right? It's a huge corpora. It has 200 pages, 200 small pages. We train an LLM. What will happen? Now I ask it a question. How do I lower the window? What will it say? Any answers on chat? I mean, I think you might be able to guess to a good extent. I think it should be fairly simple enough to see what to predict what could potentially happen. I've trained the model on the entire manual book. What will happen if I ask it how to lower the window? Any answers? Any guesses? Okay, not too many. So yeah, I think someone's putting some in the direct message, but okay. So yeah, so it'll just keep on answering. So it'll find the section. So since that will be the most closest one, it'll probably find a section about lowering a window, and it'll just keep on giving you a set of 7, 8 paragraphs without stopping, right? And it will ultimately stop because there's you probably have an upper limit on the number of tokens that you generate. So it'll stop after a few paragraphs. But that's not what you wanted, right? You wanted an answer. So now imagine we're training it on a question and answer, right? So now someone took the textbook, that manual book, broke it down into questions. Okay, so this obviously needs some data. So for example, we're doing this for an automobile company, and now the automobile company might receive calls, might receive emails about people asking. I mean, this is a really trivial example, but might come up as people saying, "How do I lower the window? How do I open the gas tank? How do I open the boot?" So these are all questions for which they might have set answers to. Now, if you train an LLM to on these question and answers, right, then you'll be able to do a great. It'll be able to do a great job. For someone next, someone asks, "How do I lower the window?" It'll just give a straight up. It'll straight up give an answer. You press the lower button on the window, on the door frame that you have, right? That's what we want. So these are the two aspects, like two I would say different corners of fine tuning on base models and on a question and answer corpus. So now, the advantages of training only on corpus is that you need low effort, right? You have the manual, you break it down into chunks, give it to the LLM, it'll learn. Now, but the disadvantage of on the corpus is that it'll keep on. The answers will not be concise and may not serve a huge variety of users. Now, with training on question and answers, the first problem is that you'll need a lot of training data. You'll need data that has been labeled. You'll need data where someone asks a question, all possible questions that someone could ask for, and then the corresponding answers, right? So that's one disadvantage. But the advantage is that you'll be getting crisp and concise answers. Okay. Yeah. So as an extension to this part, we'll go for RLHF. This is obviously a much more complicated task than what we think of it as, uh, which involves some aspects of reinforcement learning. But we can cover it in brief. So RLHF stands for reinforcement learning from human feedback. So the chat GPT that we access on the web definitely has been trained using RLHF, right? The reason we'll discuss that in the next couple of coming slides. So a method to fine tune language models. Why do we need it? It's to fine tune language models so that they follow the instructions better, are safer and less toxic, align more with human intent. So if you might have noticed, someone at the beginning of when ChatGPT just recently came out in 2022 or something like that, if you would have asked it to say, "How do I create a bomb?" right? It would have given you an answer, correct? Anyone tried out those fancy prompts to do something? For example, if someone's saying, "How do I create a medicine from scratch?" You might have gotten some answers, right? Which you're not supposed to, which are not morally correct. Anyone notice that from your experience? Okay, looks like not a lot of you are playing around with ChatGPT more, I guess. So yeah, I mean, there have been cases where people were trying to build a bomb based on the answers that ChatGPT gave, or trying to hack into things, right? For example, finding some loopholes on all these things. So they are not ethical use cases of them, right? So that's something we want to avoid. So to use all these things, we can use RLHF. So here you cannot explicitly, if you, for example, if you don't train your model specifically on this app. For example, someone on the some corner of the internet might have written, because on the internet you're not very obligated to do that, right? I can put down an article on how to create a bomb, which I'm not going to do, but I mean you can do that, right? Because you can put it down on your website, and potentially some GPT model will be trained on that data. So uh, you cannot explicitly stop it from generating such content. So that's why we need RLHF, where where you'll train the model in a reinforcement learning settings. So you will ask it to generate a bomb, on how to generate a bomb, and and the reward for generating that answer would be negative. So we want to train the model that in such a way that it does not generate anything in regards to such things about harassment, about anything that is not ethically correct, right? About hacking into companies, hacking into some databases. So a human explicitly would say, give it a negative feedback, right? And then evaluate how it does and integrate that into the model. So with a negative reward, it will understand that I'm not supposed to answer questions about a bomb, right? So there are three stages to RLHF. What is supervised fine tuning, right? Where, for example, a human will write the answers. So this is, as you might have guessed, really expensive. Where someone will ask, um, or not just for picking out harmful content, but for example, if you want very specific something like code answers, you might have heard in the news that OpenAI is now hiring programmers to generate sample snippets of code for GPT to learn on, because they've practically exhausted all the data on the internet, right? So that's how you have supervised fine tuning, where you actively put an answer. You put an answer. How do I write a Python code to find out the 78th prime number, and you write the code for that, and that is what it will be trained on. So that is the supervised part. Then you have a reward model training, correct? So there you want to give it a reward for generating the correct answers correctly, and a negative reward for generating answers incorrectly. Then you have the reinforcement learning, where you integrate that reward into it so that it generates the outputs accordingly. So that's how you can integrate some sort of human behavior into it, correct? Human behavior in the sense, answer questions as a human would do, in terms of the grammar, in terms of the way. Because you might even have noticed, I'm not sure if hopefully enough you get caught for that, but if you end up writing your college essays using GPT, it's easy to get caught, correct? There are some peculiar aspects that GPT does when generating text. So you would want to avoid that sort of things. So again, why RLHF is because it solves the problems of truthfulness, helpfulness, and harmlessness, like we discussed. PPO. Someone said, "What is PPO?" So PPO stands for policy optimization, right? It's a concept in reinforcement learning where, so if you're aware, reinforcement learning is all about rewarding, maximizing a reward, correct? So if you think of it in that way, you have an agent, and if it answers the question correctly, you give it a positive point, and if it answers it wrong incorrectly, you give it a negative. So if the model is built such a way that it optimizes the reward, so like reinforcement learning, it will try to maximize the reward, right? So it will try to answer it correctly. Now again, it's not as simple as that. There's a lot of math behind it. So you will have some equations, some functions which you want to maximize. So by doing this, that is what policy optimization means, right? So how is it different from reward model training? So it's kind of thing. I think policy optimization is a more of a umbrella term under which you have reward model training. Reward model training is where you give it a reward and it's explicitly trained on that. Whereas policy optimization covers a whole chunk of it. So there are other aspects too, not just rewards, some other ways which could potentially cover the policy optimization. So that's how you'll want the mod you'll uh, reinforce the model to do what you want it to do. Yeah. Okay. So why is that? Yeah, so it makes the models better at following instructions, right? Because as a human answer, you can give it a crisp, concise answer so that it learns to do that. Then you can, then it also helps align models with human values, not just raw likelihood. So like we see, LLMs are just probabilistic models, right? But when in some cases you would want some human touch to it. So RLHF solves that problem. Now, there are some associated challenges again, which is that it's expensive, requires human laborers. Reward models can be biased, right? So, for example, something that you say is okay to be on the internet may not be. Uh, someone else may not agree with that, right? Someone else might say, no, that thing cannot be on the internet. For example, about making how to create medicines, right? For some people might say that's helpful because it's someone can do that in case of an emergency, but some others might say that it can lead to harmful consequences where someone might not take enough appropriate care while doing that. So there can be some bias, and then it can lead to reward hacking if not careful. So reward hacking is when it tries to generate a specific type of answers all the time. That is not something you want a multi-purpose general language model to do. So these are the associated challenges. So yeah, next we have structured versus unstructured tasks. I think from now I think until now we've covered all the basics. So now we'll be going slightly towards the applications, right? So yeah, what is a task, right? For in context of an LLMs are nothing but, again, like we said, next token predictors. And this is the reason I'm repeating it so much is that it will help you maintain a context or keep bring it to your attention that for an LLM, the task is nothing but to generate the next token based on the question or the prompt. So the task is to generate the next token, and then based on the sequence, until now, generate again. So a task refers to the kind of problem you're solving, asking LLM to do. This could be answering a question, summarizing a document, extracting information, and so on, right? So different users might use it on differently, so the task varies for users. Now the goal here is to explain that tasks can differ based on the input output format and the structure of the expected response, correct? So that is what we want to discuss in this section, that is structured versus unstructured tasks. So right out of the bat, based on intuition, can someone tell me what structured and unstructured tasks would be? I think this should be a fairly straightforward question, right? Someone in the chat? An example of structured and unstructured task? Okay, no answers. All right. Structured means proper methods and ideas. Um, I think you're in the right direction, but I think we need some more context. We can I'll go to the sides. Let's see if we can get a hold of it. So structured tasks are tasks where the output. So unstructured tasks. So I'm sorry. Yeah. So unstructured tasks are where the tasks are free form text, right? So there's no strict format. A common example would be answering a question like, what is the capital of France, right? It'll give you sometimes it'll say the capital of France is Paris, sometimes it'll just say Paris, sometimes it would say that Paris is the capital of France, right? And then again, another thing is writing a paragraph summarizing an article. So if you give the same prompt twice, it'll summarize it differently, right? There's no strict format, you don't need to stick to a convention. Next, generating a poem or a story. There's again another aspect of it, right? So you don't need to, when you ask it to generate a poem, it will not do the same thing each time, correct? It's unstructured. A poem can be 3 sentences long, 4 sentences long, or so on. So how the LLM behaves in these things is that it understands the language to generate. So the model uses its understanding to generate coherent and natural text. That's all. It will try to make sure that um, the grammar is correct. Correct. That's the first requirement of generating any text in English, and then ensure that it's coherent. Right. You don't want one part of the sentence to be about one thing and the next part to be about another. Now the analogy of this is to like asking a person to explain something in their own words, like flexible, creative, and varied responses. If I ask you, each one of you ask you what you understood from this presentation, or what you understand from an LLM, right? So each one of you have a different answer, and all of them could be potentially correct, right? There's no right or wrong answer. So given a page from a medical document, extract the patient's name. This is one task. Another is generate a limerick. So, which one of these do you think is a structured task, and which one's an unstructured task? We can hope for some answers in the chat box. One is structured. Okay. Um, actually, this was sort of a trick question, so I'll tell you the implications of it. Let me see. We can go to ChatGPT and try it out here. Okay. So first question was from a page. So this I've cropped out from a medical document. Obviously, it's masked, so you don't need to worry about the patient information. So this is an image. So this has the patient's date of birth and all. So now we want to extract this, correct? Patient's name, date of birth, marital status, race, and religion. I will put this, bring this. Okay, looks like I'm not able to. Okay, I'll just take a screenshot of it and put it in the chat GP. So I cropped it, put it over here. So now I want to ask the same thing. So just to give you a feel of what it does, I'll give you the exact same task. Yeah, let's see what it gives. Okay, so this is how it gave, correct? So now I'm hoping this goes right. Let's see. We'll open another window of ChatGPT and do the same thing again. So let's see if it will behave in the way that we want it to. The screenshot that we just pasted. So okay, I'll just to ensure that the output is what you want. In sections is what I said, right? Now let's see. Okay, unfortunately, it gave the same answer. But tell me one thing though. Uh, okay, let me say in JSON. Yeah. So can you tell me what could potentially be the issue with this? So now we can see that here for the same question we did get. So in the first go we got the same answer, which is kind of predictable because it was trained to probably give it in that way. But for example, I asked the same prompt to probably for some other LLM called Claude, right? It might potentially say patient name. The patient's name is Catherine Yu, and its her date of birth is this, and so on, as a paragraph, right? So, what do you think might be the problem with this? Since you're all I mean, associated with programming or technology in general, you might also see one common problem with it. You're right that this is a structured task, but what could potentially lead to problems here? Any guesses? No proper format or structure, exactly, right? So I think some of you might relate to this if you have been working on applications using machine learning. But JSON, so you can assume that right now there are other formats like XML, but JSON is the standard method to handle structure, correct? So you can have patient name, and this is common across anything. So this can be read across multiple languages. Every programming language that you have will have a way to handle JSON. You can read it. You can read patient name. You can allocate it dynamically. You can do anything with JSON. But with such text, you cannot do that. Someone could say this. Someone could just give the first two. You can give it as a passage that the patient's name is Catherine Yu. Her date of birth is this. Her marital status is this, right? So parsing it is a big problem. So that's why, although the task is structured, to always make it to have it generate always in a constant fashion, you have to say in a JSON format. So if you ask it to do a JSON format, this will always be fixed. Now this truly becomes a structured task. This does not change across calls, hopefully, assuming it doesn't hallucinate, right? So this is a classic example of structured task. Now the second one was generate a limerick. Does anyone know what a limerick is? So it's like a short poem. For those of you who don't know what, I can just what is it? Consisting of 5 lines. Right? There's a specific type of prose or poem, right? Which is there was once a man from Peru. So you can see that it follows the AABBA rhyme scheme. That is Peru, shoe, fright, light, and then again the true first one, right? So this was just an example, but yeah. So our goal was to say generate a limerick. See here, now it gave this one. And now let's try to ask this to this one, generate a limerick. Yeah, so you can see that, right? It's a different thing. This one says a club younger coder called Lee wrote programs while sipping on tea. This is again completely different. This was some young coder from old Kathmandu. So here we can notice that there is no right answer to it. This is an unstructured task, correct? There can be different answers and not necessarily, and all of them could potentially be right. Yeah, someone on the chat box says is there any difference between JSON and pandas? I think the comparison itself is flawed, right? JSON is a way of is probably a notation, right? As the name suggests, it's a notation to represent structure, whereas pandas data frame is a data structure, which is very different from this, right? Pandas data frame is so what's exactly your question between JSON and pandas, which is a library? You can even unmute Rajshekar if that's more convenient. Okay. Okay, can be mute. Okay. Let me see if I can find you. Yeah, Rajshekar. Um, okay, I'm not sure I'm able to do that. Okay, looks like it's not really working out. Unmuting. Okay, but okay. Okay, I'll try to explain your question as best as I can. So JSON
Can
is
you
a
hear
structure.
me?
Yeah, I can hear you. Yeah.
Yes. I just asked whether these things can do it in pandas.
So I think I'm not sure I get your question because, for example, see, JSON is a common structure. For example, if you've learned about internet protocols, HTTP, everything you see on the internet travels across. When you send a request to a web server, when you hit Google, right? It sends a JSON data request payload to it, and then you get a response to in a JSON payload again. So uh, so how you handle it is up to you, obviously, right? You can ask it to generate, for example, I mean, if I'm not, hopefully that works out, so I can ask this. uh, Extract the same page name in an XML format, right? Which is another way to handle things. So here you can see that it gave it as an XML format. And honestly, if you want to say it as a pandas data frame, as a pandas, you can see that it represented as a data frame, right? So you can do that, but it's just that the structure needs to be fixed. You need to have a predetermined structure which you want to work on. Got it? Does that answer your question? Yes. Okay, cool. Yeah, thanks. Someone else said, how does next token prediction take place in unsupervised learning? So Abdul, I mean, I get that it might be difficult to understand considering that we're not training it for explicitly for that, but you understand that there are some common rules of context, grammar, and verb noun positioning, right? In English, correct? So the next word prediction happens based on that. When you ask it to say generate a poem or generate a story, it will generate it based on its initial pre-training. So when you said unsupervised training, it doesn't mean even when you're doing unsupervised training, you start with the base model, correct? The base model itself has some English, some capabilities of creating proper English sentences. So when you're doing unsupervised learning, it still sticks to that basic English rules while trying to accomplish your task. So you don't need an explicit label for that, right? Hope that answers your question. Yeah. So I mean, so the to answer your question, Rajkumar, so in an ideal also, if I were to write it in a JSON format, then in this case, the first one would become a structured task, the second one become an unstructured task. Make sense? Yeah. Okay. Hopefully that does. So this was the task one, and second task is again we have to generate a limerick. So I think we just okay. Can you explain about task two? Ashika, task two was about creating a limerick, right? You have to create, or in other words, create a poem. Anyone can have a different poem. You can create, one person can write it in one way, another can another. Limerick. I'm not sure if you are following that, but it means a 5-line poem, which has an A B A B A B B A. I mean, if you want to look at it, can go for this. Yeah, Rashik, if you can see the screen, it says there was once a man from Peru who dreamed he was eating a shoe. Right? It's a poem. Yeah. Okay, we'll go back to the presentation. So I think we went ahead. The structure task is when you want to get it in a specific format only. That's something that is machine readable, like JSON, lists, tables, key value pairs, right? Extracting structured information from a resume. Examples are converting user input into a database query. So, like for example, someone wants to say, I want to see all the. You have a database, for example, that has all the patient names from a hospital. Then you want to see, I want to see all the patients that are still admitted, right? So you say that, and the output of the LLM would be an SQL query, possibly, right? Which say select star from patient's database where status is still admitted, correct? So that's again, it has to be a structured task. Categorizing text and assigning structured labels, for example, sentiment analysis, or when you're trying to do some classification tasks like that. So here the LLM behavior is such that it wants to follow some specific instructions, formatting instructions to produce consistent structure. And in most cases, we want the answers to be always the same and reproducible, right? So you can you can ask your prompt saying, format your response as a JSON. Yeah. So these are again potential questions to ponder, right? So these are really interesting questions, which are again topic of some research areas right now. Right? That is, can you get the exact same output each time? What do you guys think about it? For example, if I ask an LLM to do the same thing multiple times, 5, 6 times to different LLMs, will the answer always be same? Yeah, no, that's correct. But any idea why it will be no? So I think we did talk about this at the, I think, until now in this presentation. So a simple answer would be that LLMs are no depends and maybe different initial weights. Not really. So different initial weights is definitely a different thing, because once you have, so for example, the GPT that we can see here, for example, this one. Now what we are seeing in the background has the same model. So there's no point of having different initial weights. Whatever you say is on the same model. So that's not exactly what we're going for. Depends and maybe the essence may not be same. No, okay. The simplest example was this, right? Actually, that's even an even interesting question would be this. Abdul, no, even barring the format, even without the format. So here we asked it to generate. Let me see where it went. Yeah. So here we asked it to generate in an XML format. It gave this, correct? Now, because we did ask some questions in the middle, it forgot to add the patient's date of birth and all. But in a sense, like we talked, they are probabilistic systems, right? LLMs are probabilistic systems. They have some stochasticity in it. So, like I talked about that gradient descent algorithm, right? The push can be random at any point of time. Similarly, if you have a high temperature, correct, and you ideally can't set a zero temperature. Even if you were to set a zero temperature, there is some level of stochasticity, some amount of randomness. For example, okay, here after writing the patient, it could have been name, it could have been date of birth, it could have been age, but it chose name, right? Because out of the next token predictors, name was the one that came in the first. Now, if you had a higher temperature, date of birth would have come in first, could have come first, right? So because of the stochasticity of that randomness induced by temperature or some other hardware aspects, we cannot always get the same answer, and that is why you cannot rely on LLMs to make solid decisions. Because right now, actually, I can show an interesting experiment over here. So let's create a new chat. I'll ask it to say, um, okay, let me think of an example where we can test how information might change. We cannot rely on LLMs, right? For example, who is the best actor in India? Let's see. Okay, I'll try to stop it there. Okay, so it's trying to list out these things right now, because this is the reason you cannot rely on factual data for this, right? Now I'll say no, but So here it says Irfan Khan in the first one, right? Critically. So I'll say no, but the best actor is Salman Khan, for example. I'm asserting that. Fair enough. So now it says Salman Khan definitely has a full. So it's not that it's not it's only going to agree, right? So GPT was made in such a way that this again might differ, but to agree with what you say. So even if you try to insert, maybe here it answered immediately, but for example, if I try to say no, this person is absolutely the best actor, it'll try to agree with me. So that is why you cannot rely on LLMs to make critical decisions as of now, right? And again, reproducibility. Now if I ask again who are the list of best actors, they can say something. So you cannot tell someone that if you want to find who is the best actor is go to ChatGPT, ask it to list the best actors and find the first one. It's not going to be reproducible. The next time around it can possibly say Shah Rukh Khan as the first actor, right? So that's the reason we cannot rely on LLMs, and that's a potential cause for having reproducible outputs, right? You want to be able to trust it, right? So when you just like you trust a calculator or you trust Google to give the right answer each time, or at least a similar website, that which is what. And now reproducibility is a challenge because without this stochasticity and the answers that an LLM generates might be bland, right? So you want to somehow be able to ensure reproducibility without changing the other parameters, which is a proper research direction where there has been a lot of research being conducted around this area. And again, there is some dependence on hardware. This is probably out of the scope of this presentation, but when you ask ChatGPT to do this, you might not get here. You would get it in the API key when you're using the API, but there are millions of people using just ChatGPT, and the same model may not be given to all the million people, right? So there is some fingerprint to as to which hardware OpenAI is using, correct? So based on the hardware specifications, there might be some change, might be negligible, and sometimes might not be. There are some change in the output. So that's one other aspect. So we do have a few other slides to complete, but since we're running out of time, I think this is a good time to stop this one. I think the next part of it is absolutely critically important. I think I would want all of you to be with the max of to the best attention possible. So we can take some questions right now before we go on to the next hour. I mean, possibly after the break. And then again, we'll definitely have some practical examples over there. We can finish the rest of the remaining part of the presentation in the next session, and then move on to some practical and some practical use cases. Yeah. So until then, any questions? So someone asked how to make unstructured to structured format example. So yeah, one good way to make it structured, right? If you want to write code which ensures the same thing every time. Now you can say, please generate the limerick in a JSON format as follows: line 1, line 2, and so on. Right now, you kind of broken down it into a structured part. Okay, I guess we checked exceeded the chat, so we can just do this here. So now you can see this. No, fill in the lines. Create a limerick. So you can see a man from Mary who dreamed of eating a shoe, right? So here now it's a structure. Now every time you ask it to generate, it'll do this, and now you can write code to parse this, like line 1, line 2, line 3, line 4, and 5. You can use it, pass it accordingly, change it, flip it, anything you want. Can you give some information about the system configuration that we have to use for LLM or medical images, including GPU based? So again, that depends on what you want to do. I don't think it will be possible for you to. I mean, I'm not sure about what you plan to do, but for you to be able to do these medical image processing, you'll need super high LLMs, and for that you'll need really high GPUs. For example, GPUs. I think the best advice I could give to you is using this thing called RunPod, RunPod, where you can rent out GPUs. Right, you'll be charged by the hour. you can access it. It's a remote machine. You can use it. You can access LLMs. That's what I would do if I were you, right? If I want to run some task, I can rent out a GPU, do it per an hour basis, and then give it out. I'll be only charged for the time that I use. You can check that out, run project. Yeah. Any other questions before we go for the break? You can use this for it's more like you get access to the machine. So I'm not sure if you're aware of the concept called virtual machines and virtual machine. So basically you get a virtual machine where you can in your laptop. I think it's really difficult for you to do that. Uh, you might need GPU memory exceeding 50 GB, and which is almost impossible for a laptop. So for you to inference a completely big full LLM on your own machine, it's almost impossible. You'll need to use super quantized versions or super small LLMs, which might not serve your use case. You can always go for this 8 billion models by Meta Llama, but I'm not sure if they'll serve your use case. You can go ahead and use that. Yeah. Yeah. So any other questions? LLM in images. Yeah, I think we can do that in the next session. I think we do have a small part of it covered, so we can have the discussion then. We will discuss about how an LLM process images, right? Because ideally it was built to handle text. We'll see how it handles images too. So yeah, looks like we're at the end of time. Then I think are we good for to take the break?
I think we are like, okay, the session is done. Thank you so much for such an interactive session. The approach, I think, is truly appreciated by all of us.
Yeah, thanks.
I
That's
I would also request you to kindly share the slides so the
sure.
participants can refer to them before we move to the practical session.
Okay, sure. I can do that. Let me see how. So should I send the link to you and you can forward it to all the participants?
You can either send it here or you can send it to me personally on WhatsApp or
Um,
email,
okay,
whatever you prefer.
let me check if I can do that. So I'll try to download it. Um,
You can either share the link also, that would also be fine.
yeah, I think with the link, I think with participants, I'm not sure if that will be a better option. I can just quickly do because they might try to edit it, so I can just download a presentation here, yeah, and send it as
Okay,
a file.
okay. You can do that after the session, after I end the meeting. That would be fine.
Sure. Actually, you know what? I think I'm not sure if so that people can just download it. I'll just try to send it right now. Attach it as a file right now. Yeah.
Okay,
Give me a moment. Yeah.
okay.
Okay. Yeah. I think I was able to attach it. Let's see. Yeah. Is everyone able to access it? I can. So, if someone can try to download it and confirm that they're able to access it.
Yes. It is accessible to me.
Okay. Perfect then. So yeah, I think we can continue with the remaining parts of the rest of the section in the next session. Yeah.
Okay, yes. We will meet again at 2:30 p.m. for the
Yeah.
practical test.
Sounds good. Yeah. Okay. Thanks everyone. Yeah.
Okay, thank you.
Thank
Thank you
you.
so
Thank you. Bye.